Hello students and welcome back. So now we are going to talk about the digital system design flow. That means what are the different techniques that we use for designing a digital system. So in this video we are going to talk about the digital system design flow, the steps involved in the system design and the steps involved in the FPGA implementation of the same system. So let us get started. So first of all, we are going to talk about the ASIC design flow. ASIC is application specific integrated circuit. So here, first of all, we are given the design specification. That means this is the circuit you have to make. You have to make a controller for a drone, or you have to make a Bitcoin miner. So that is the specification. Then we work on the architecture design. That means what kind of coding techniques will be used. Once that is done, then we go for the RTL modeling, register transfer level modeling. That means the circuit is ready now. Once the circuit is ready by the simulator, then we go and synthesize it. Synthesis means converting into an actual circuit. Once that is done, till this point everything is software based. It is all simulator based. We are getting the estimate that how much area, power and delay my circuit is going to have once it is fabricated, but it is all software. Then we go for the physical design and we talk about the layout and fabrication. Once everything is finalized, then we fabricate it and the chip is ready. This is the complete design flow that we use for any circuit design. We had talked about front end and back end. The first four modules, that means design specification, architecture design, RTL modeling and the synthesis, they are mainly the part of front end. Whereas physical design, layout and fabrication, they are on the back end side. Let us talk about the design hierarchy that we use. We mainly use the divide and conquer technique. That means we are going to divide our larger tasks into the smaller ones. We are going to generate the leaf nodes. A leaf node refers to a subsystem which is a part of the larger system. We will discuss these when we discuss that how to divide your larger systems into subsystems. We are going to identify these leaf nodes, connect them, and that is how our design approach become easy, and then we are able to build the larger circuit. Let us talk about one example. We are given to implement a 4-bit adder. A 4-bit adder is going to add two numbers A and B. Each of them is of the length 4 bits. The output is also going to be of the length 4 bit, and there is a possibility that the carry will be generated. So now we may look confused. Then we think, I can perform 1-bit addition. How do we connect different 1-bit adders and make a single 4-bit adder? That is how we divide and conquer. We decide the leaf nodes, design them, connect them and make the larger circuit. Let us talk about an analogy. You are given a task to design a car. Well, that is a huge task. But then you say, okay, one team will work only on designing the body. One will work on designing the engine. One will work on the interior and one will work on the electronics part. Now, the team which is working on the engine, they will be working completely on fine-tuning the engine, adding the gears and all the things that are required. The team which is working on the electronics control will be dealing with the circuits and all the connections. The team which is responsible for the body design, they will be working on the type of metal to be used, what should be the strength and what should be the length, width and all these things. And eventually all of them will combine their output and one car will be generated. This is how we work for the digital system design as well. So now let us talk about these individual tasks. The first one was RTL design, the register transfer level. Here the RTL is used in the logic design phase of the integrated circuit design cycle. RTL abstraction is used in the HDLs to create high level representation of the circuit. We are going to write some code using the text based coding, and RTL design will convert those text based codes into the circuits. Lower level representations and actual wiring can also be derived using the RTL design. RTL design also helps us in area power consumption estimation. We can also know what will be the estimated speed of operation of our circuit. The next aspect is logic synthesis. In the logic synthesis, we are going to convert the RTL design into the design implementation in terms of logic gates. Some of the tools target the synthesis for programmable logic arrays, PLAs, and few focuses on the implementation using FPGAs, which are field programmable gate arrays. In our training, we will be focusing on FPGAs as they are much more advanced than the PLAs. We are also going to deal with adding clocks and memory element in the logic synthesis stage. And we also work with optimization techniques so that minimum area and power requirements are matched for the circuit implementation. The next aspect that we have is the physical design. The circuit representation of the components are now converted into geometric shapes. These geometric shapes are also called integrated circuit layouts. So now we have the layout for the circuit ready. In this complete process, we have a few steps involved, and these are floor planning, partitioning, placement, clock tree synthesis, routing, and the physical verification. The next task that we have is the layout design. Here we are going to talk about the actual fabrication, how different metals and semiconductors will be arranged in the semiconductor die. So we are going to have the representation of our integrated circuit in terms of planar geometric shapes. These shapes will correspond to the patterns of metals, oxide, or the semiconductor layers. Historically, this process was called the taping process, and we have interaction of many chemical, thermal, and photographic variables, and they need to be very carefully controlled while designing the layout of the complete system. So now let us talk about the design flow for a system using an FPGA. FPGA, as we had described, they are field programmable gate array. FPGAs are reconfigurable units. That means the single hardware board can be configured as any digital system by programming it with different codes. First of all, we are going to have the design source file. The design source file is going to be our Verilog file. Then we synthesize the text-based coding file into a circuit. Once that is done, then we implement it using the design implementation step. Once that is done, then we generate a bitstream file. This file contains every possible information of transforming our design and converting into a circuit on FPGA. And then we upload it on the FPGA. And now this FPGA will behave like the system that we have programmed with. Next time we can reprogram it and it can work as a different system. So students, this is the process that we follow, and this is what we are going to do in our training program. We are going to focus on the design source file, that means how to write the Verilog code, how to synthesize and implement, and then convert it into a bitstream file and upload on the FPGA, and then we will test whether the FPGA is working as per our system requirements or not. So students, now we have talked about the coding. So in the next video, we are going to talk about the Verilog programming language. Keep learning. Thank you.